It links to my title of the lecture, which is The Penis of Statistics. I have an unpleasant habit of mentioning penises, and this year I thought I'd theme a whole lecture around the penis. And why not? The unfortunate thing is I noticed if you put a colon in the title after the word statistics, it's kind of saying Andy Field is the penis of statistics, which some people would probably agree with. Anyway, so what we're going to do today, basically I'm going to go over 5 key concepts in statistics. So this is kind of a bit of revision, but as I said, a lot of these early lectures are me trying to go over things that those of you that did research skills will be familiar with, but giving you my own sort of spin on them. And it also serves as an introduction to these things for people who didn't do research skills last year. So the penis comes from an acronym, because I think that the 5 key concepts in statistics, basically, if you understand these, you understand everything, are parameters, estimation, null hypothesis significance testing, which you won't necessarily have heard it called that, but that's all that p-value crap that you did last year. Confidence intervals, but I just call them intervals because otherwise you don't get the acronym of penis, and standard error. So I'm going to go through these 5 concepts in turn, and not necessarily in that order, and basically by the end of this lecture, I think that means you should understand everything that's worth understanding about social science statistics. So normally that sort of typifies the average person's reaction to doing a statistics course. And as I was trying to say last week a bit, I think this is because people overcomplicate statistics. They focus on the differences between everything, and they don't sort of hone in on the sort of fundamental things that all the models that we use share. So this lecture is about dealing with the 5 key concepts which I think you can latch around any sort of model that you fit to data. So I also said last week that basically there's only one equation you ever need to really understand, and that's this one. That in psychology, what we're trying to do is predict outcomes from some kind of model, and that model won't be perfect, so there'll always be some error of prediction. And we looked at various examples last week, but I also mentioned that on balance, most of the things we do are basically regression, so a linear model, and we looked at this equation here, the beta 0 plus beta 1 x1. So you can predict an outcome from a predictor variable x and some parameters. So these b things are called parameters. But, they're just numbers, really. When I'm talking about parameters, I'm talking about these betas, essentially. So I think the acronym PENIS represents everything that you need to know. Once you've understood that the models we fit in psychology are basically all linear models, they're all that beta 0 plus beta 1 x1, then there's some fundamental things that are true for any model that has that form, that has that linear form. The first is it will be defined by parameters. So as I just showed you, and as I've mentioned before, there are these betas, there are these numbers in them that tell us something about, say, the relationship between the predictor and the outcome, or whatever. It defines the model, essentially. So every model, or every linear model, has parameters, or has these betas, or coefficients, whatever you want to call them. Call them Bob, if you like. Now, these parameters have to be estimated. So estimation, or at least having a vague grasp of how they're estimated, is useful. But also, the E could stand for error, because that's another important thing to understand. So understanding the error in the model and how we can use that error to get an idea of the fit of the model is a useful thing to know. And again, it applies to any linear model that you choose to fit. Now, when we talk about estimation, why do we say that parameters are estimated? Well, it's all down to this idea that we talked about last week of we don't have access to the population that we would like to make predictions about, so we use samples. So what we do is we calculate the parameters in the sample. So we calculate the mean, that's a parameter, or we calculate a beta value like in regression. And we use that beta in the sample as an estimate of the actual value in the population. So when we talk about parameters being estimated, this estimation process is simply due to the fact that we're using samples to try to tell us about a population to which we don't have access. So we cannot ever know what the actual value of the parameter is. We have to estimate or approximate it based on the sample. any any parameter you have can be significance tested. So significance testing was, you would have been taught a lot about it last year. So that's, this idea of looking at p-values and things like that. So you can significance test any parameter in various ways. So we'll talk about that. You can construct confidence intervals around any parameter. So any model you fit, it has these parameters. The parameters you can have confidence intervals for, as well as the point estimates of them. So as well as estimating a single value, you can estimate a range of values, which is known as a confidence interval. And also, another key concept is the standard error. And the main reason it's a key concept is because to get these confidence intervals, it's all based on the standard error. So the standard error tells us something about how well our parameter estimates the value in the population. So we're going to look at all of these things in turn. But as I said, I think any model you have, these 5 things are important, and they apply to any model that you have. So let's have a look at a simple example of a parameter. Now, I think, or when I was learning stats, I found the word parameter quite scary because, I don't know, it just doesn't make a lot of sense to me. But so to kind of keep things really, really simple, we'll look at the simplest example of a parameter I can think of, which is the mean. And as I said last week, in statistics, we're trying to fit models to our data, and we want that model to represent what's happening sort of more broadly than the sample that we have. So we calculate a value in our sample and use that as an estimate of what the true value in the population is. So we fit a model. That model can be as simple as just fitting a mean. So that's what we're going to stick with. A very, very straightforward example looking at the mean. You might not think intuitively that the mean is a model. You might just think it's a description of something. And in a sense it is, but it's a model from the point of view that it's not a value that we actually have to see. In the data, it kind of gives us a summary, and we can use that summary in a very basic form to make predictions. They're pretty crap predictions, but we can use it nevertheless. So it's a very, very simple example of a statistical model. It's a simple example of something we can fit to the data and be better at predicting the world than if we didn't have that value. So I said last week, we can characterize the mean as a model, and all it really means is that we're estimating a single parameter. So we don't have the beta 0, we don't have a predictor variable, we just have one parameter, which I've called b here, but sometimes you'll see the mean as, in fact I think I interchange a bit in my slides, which is probably not very good. Sometimes you'll see the mean as an x with a bar on the top, but I'm using beta here. So we looked at an example of cloaks of invisibility, and do they make you more mischievous? So we could get some idea or make some prediction about levels of mischievousness just from the mean. Now the first example I'm going to talk about is to do with weddings, actually, because last year, I think, or maybe the year before, there was a news article, and I like news articles as examples, and it was making a big fuss about the fact that the average age for marriage in women had become 30 for the first time ever. So I think in 2005, the mean age of marriage for a woman was about 28 or so. And then a couple of years ago, the Office of National Statistics had discovered that it had gone up to 30. And the newspapers were making a big deal about this. On average, women are not marrying until 30 now. Now, if you look at men, it turns out that the average age that a man gets married is about 31. It might be 31.7, something like that. So we can use these averages, or you can call them a model, and you can use them to make predictions about the world. So let's make a prediction about me. So first of all, hands up, who thinks I'm married? Oh, do you know what? I love you so much more than the cohort last year. So when I asked that question last year, there was not a single hand went up. And it did make me think a little bit that they were bastards. But you're nice. So you're making a prediction that I'm married. Now, what is that prediction based on? Because, I'm a I'm a statistics lecturer. I can barely speak at 9 o'clock on a Wednesday. So, why would you think no one wants to marry a statistics lecturer? Trust me. Oh, did I? Yeah, that's why you should never rewrite your lectures. Right, well, another way that you could have maybe made a prediction on that is based on my age. So knowing that the average age for a guy to get married is 31, I'm a reasonable bit older than that. So you might think, well, it's reasonable that I might be married. I'm more likely to be married, for example, than, say, a 15-year-old. Hopefully. But we can also, okay, let's kind of flip the question round. So the average age for a man to be married is, whatever I said, 31.7. What age, did I tell you this last week? No. What age did I get married? If you had to guess, based on no evidence whatsoever. 30. Yeah, that's a reasonable guess, because the mean's about 31. So, if I was an average kind of person, I took my wedding ring off just to try and fool you. And, I mean, what's the point? What's the point when I've already told you the answer? Yeah, so 30 is a reasonable guess because the mean's 31. So it's that means that obviously sort of the peak of the distribution is around there. So 30 is a pretty good guess. You can use the mean to make a prediction about what age I got married. I'm a man. On average, men get married at about 31. So the bulk of the distribution is going to be around that value. So 30 is a very, very good guess. So the only point I'm trying to make here is that we can use the mean, even though it's a very simple and basic statistic that people understand, we can use it to make predictions. You can predict that I probably got married around 31. But there's going to be some error in that prediction. So actually, I didn't get married at 31. I got married last year. Oh, I know. It's much nicer than when I go on about penises. So I got married last year, and I was, how old? 38 at the time. So I was quite a bit older than the mean, but not too much older. But the point is there will be error. So you can make a prediction. It's a reasonable prediction based on having a model, and although that model is quite simple, but there'll be error. So in this case, there was an error of about 8 years. So the mean is a statistical model. Now, we know, hopefully, that the mean or the average is just the sum of scores divided by the number of scores that you have. And you can, if you're into equations, you can write it like that. So I'm not going to dwell on this, but if my pen works. My drawy pen thing is not working. Come on, drawy pen. Never rely on technology. But the top half, which I was going to point out on the screen, but I'll just point with my finger. The top half up there is just saying add up all the scores that you have, and the bottom half is just n, the number of scores. So it's a very straightforward thing to understand, but it's still, nevertheless, a simple model. You can make predictions about things. So let's look at an example. As I alluded to earlier, statistics lecturers don't generally have a lot of friends because, we tend to corner people at parties, and, well, we don't generally get invited to parties, but if we do, we corner people at parties and start going on about heteroskedasticity and just don't invite them back. So we got 5 statistics lecturers, and we measured how many friends they had. So and here's the data. So the first statistics lecturer had 1 friend. That was his hand. The second one had 3. Third one had 4. He was pretty popular. So if we wanted to work out what the average number of friends is, we can just add up all those scores, which gives us 13, and divide by the 5 scores that we had. So we end up with this value, 2.6. And it's a hypothetical value. There's no one in the data that actually had 2.6 friends, because that would be a bit weird, even for a statistics lecturer. But we can use that to make a prediction. So, for example, if we came across a new statistics lecturer, like Professor Hippo. Hello, Professor Hippo. I'm not very good at ventriloquism. Hello, Professor Hippo.
Hello.
We'd like to know, or we're going to make a prediction, Professor Hippo, about how many friends you have. And I reckon that you've got 2.6 friends. But I don't think that's true, because you wouldn't have 0.6 of a friend, because that would be like having a pair of legs in your fridge or something. So you've probably got 2 or maybe 3 friends. You're probably around the mean. So 2 or 3, am I right?
No, I've actually got 2.6 friends.
But that would make you a psycho, Professor Hippo.
Oh, I'm a psycho.
It's like I was saying last week. Never underestimate the power of the pink hippo. So there's error. There's error. Unless you've got a psycho. So we can use the mean as a model. We can make predictions based on the mean, but there will be some kind of error. So if we rearrange this model a bit, we can work out what that error will be for an individual. So say we had someone and we knew for a fact they had one friend, so we can replace the outcome with an actual value of 1. We can work out what the error is associated with the prediction for that person. And these errors are important in trying to make an assessment of whether the model is a good fit. So how do we measure the fit of a model? Well, we basically use these errors. So something like the mean or any model we fit is not a perfect representation of reality. There's going to be some error associated with it. But we can use these errors to tell us something about whether the model is any good. So in an ideal world, models will be perfect. So this would be a kind of an example of a perfect fit. So every data point is exactly the same. So if we calculate the mean of it, we get a value that's the same as all the data points. So every data point falls exactly where the model would predict it falls. So the dots are all sitting nicely on the line. That would be a perfect fit. That never happens. Never ever. And if it does happen, it's weird. It means all your scores are the same. So what you tend to get are things like this. So these are ratings of Britney Spears' album Britney. I got these off of Amazon.co.uk. So you've got ratings out of 5. The red line along the middle is the mean. And there you go. You can see it's not a perfect fit. So the mean doesn't perfectly reflect everyone's ratings. Some ratings are a fair bit higher than the mean. Some ratings are a fair bit below. Now, an interesting thing that not a lot of people know about Britney Spears is the music that I listen to, quite heavy music, and lots of people sort of think there are subliminal messages in the kind of music that I listen to, but I don't think there are really. But Britney Spears does have one. So I discovered this when because my wife likes Britney quite a lot, and I reversed "Hit Me Baby One More Time." So I put it through some software that reverses it. And there's actually a hidden message. Now, you may not know what that was, but it's actually, I wrote it down to remind myself, it's pretty scary. It's worship Satan because he is your dark lord and master. Sacrifice goats to your master Beelzebub. Now listen to it again.
Worship Satan, for he is your dark lord and master. Sacrifice goats to your master Beelzebub.
That's some scary shit right there. So how do we calculate error? How do we calculate fit? Well, what we do is we use what are known as deviations. So deviations are just the difference between what you predict from your model and what you actually observed in the data. So it's pretty straightforward. A deviation is just the score, in the context of the mean, it's just the score you observed, that's the xi, minus the mean, which is the x bar. So it's just the different, you can generalize this, if you're not looking at the mean, to just what your model predicts minus what you, the other way around. What you actually observed minus what the model predicts. So it's just a difference between prediction and what you actually got in your data. So here's our lecturer data again. So you can see there were 5 lecturers. The black dots are the 5 scores of those lecturers. And the mean, so the model that we were fitting was the average, which was 2.6. So the black horizontal line is our model. That's our prediction. And the black dots are what we actually observed. Now the red hashed lines show the deviations or the differences between prediction, the horizontal line, and what we observed, the black dots. So these are errors or deviations. And another thing that happens it's really irritating, or I think it's irritating, is in statistics there are lots of different terms for the same thing. So we use the term deviation, which basically just means error, which basically is also the same as residual. So you'll see these terms, error, deviation, residual, used in different contexts, seemingly masquerading as different things, but actually they're basically the same. A residual is just an error, a deviation is just error. So it's just difference between predicted and observed values. So we've got some errors here. So for the first lecturer, for example, we overestimated the number of friends by 1.6. So he actually had one friend, but we predicted he had 2.6. So there was an error of minus 1.6. So if we want to work out the total error in this model, so the total error across all the sample, we could just add up these deviations. Now, what would be the problem with adding up those deviations or those errors? Yes, they would cancel out. Would you like a chocolate? I'm afraid the box of chocolates got hit quite heavily in my office last week. So there's not that many nice ones left. Quite a few eclairs. I can never get that excited about chocolate eclairs. Yeah, so if we add these all up, they will cancel each other out. So we can demonstrate this. If we just wanted to use the total error, then we'd end up in a situation a bit like this. So we've got our scores. So these are the number of friends for our 5 lecturers. Our model, or the mean, so the prediction we make is the same for each one of those. We predict 2.6 friends in every case. And if we work out the difference between the two, we get these deviations. So this is just a table that has the same numbers that were on the graph. So if we add up those deviations, we get a 0, because the mean sits in the middle of all the scores, so those errors cancel each other out. So we can't just, if we want to know the total error in the model, we can't just add up the deviations because of this whole plus minus problem. So anyone know what we do instead? Yeah, well done. We square them. Fudge. Was it you who said it as well? Oh, sorry. So we square them instead. And what squaring does is gets rid of the plus and minuses. Now, squaring is just one way you can get round this. So there are other things you can do, but this is just what gets done most of the time. So rather than using the sum of errors, we use the sum of squared errors. So to get over the problem of deviations cancelling out, we square them and then we add them. And this gives us what's known as the sum of squared errors. Now this is a very, very important concept, because everything we do, quite literally actually, everything we do on this course will involve sum of squared errors at some point. So it's important that you understand that sum of squared error is just, it's sort of a measure of fit, really. It's a measure of how well our model is fitting the data. So it's the difference between kind of, you know, what we're predicting, what we observed, but we've sort of squared it and added it up. So it's just a sort of a total measure of error in the model. So this is the same table as before, but now we've squared the deviations and we could add them up to give us the total squared errors that we have in the model. Now this is not, you know, this is quite a reasonable thing to do, and as I said, in lots of the tests that we look at later on the module, you'll see sum of squares cropping up all the time. So it is used a lot. There's one potential problem with it, which is, so we've got 5 scores here, and we end up with a total sum of squares of 5.2. What would happen if we, say, added another 5 squares? What would happen to the sum of squared errors? Yeah, we'll just get bigger because we've got more scores. I've only got eclairs left, I'm really sorry. But even eclairs need love. So because we're using a total, if we just had lots and lots more scores, we'd get, you know, a bigger amount of error. So sometimes what we do is we take the average amount of error. So this just offsets the fact that if we use the sum of squares, it's dependent on the number of values we have. So sometimes you'll see, in the context of the mean, it's called variance, but in the context of other tests, you'll see something called a mean squares, and that's just the average sum of squares. In the context of the mean, though, we call it variance. Again, in a way, I mean, it does make sense that it has its own unique name, because it's slightly different from a mean squared, but the principle is kind of the same. We've got either a total amount of error or an average amount of error. So we can use we can use the average amount of error as a measure of fit. So in the case of when we're looking at the mean, as I said, we call it variance, but all we're doing, we're taking so this equation's starting to look scary, but essentially the stuff in brackets, that's the deviations. That's quite a simple thing to understand. It's just, you know, what we predict subtracted from what we observed. The squared thing just means we square those deviations to get rid of the error, and then the squiggly squiggly sum sign thing means that we do that for each data point and add them up. And then at the bottom, the n-1 is just basically we're taking an average, but it's a slightly elaborate average. So we use n-1 rather than n. The problem with variance as a measure of fit of the mean is that it's, because we've squared everything, it's now in units squared. So in the case of our number of friends that someone had, we've got number of friends squared, which doesn't make an awful lot of sense at all. So again, sometimes this gets expressed as the square root of the variance, which just converts everything back to the original units of measurement. So sometimes you see people talking about a standard deviation. But all these concepts really are kind of the same. So you've got sum of squares, that's the total error. Variance is the average error. Standard deviation is the average error, but expressed in the original units of measurement. They're all sort of basically expressing the same thing, but in slightly different kinds of ways. So the main point I'm trying to get across here is that you can fit a model, there will be error in it, but you can use these errors to give you some idea of whether the model is a good fit or a bad fit. So the standard deviation, which is probably something that, even if you didn't do research skills, is maybe something that you're familiar with, is simply a measure of fit, really. It's a measure of whether the mean is quite representative of the data or not very representative of the data. So here's Brittany's data again, so ratings from Amazon. Now the standard deviation of these ratings turns out to be 1.73. And that's reasonable. You've got a range of 5. You can give it like 1 star, 2 stars, 3 stars, 4 stars, 5 stars. So there's only 5 values that you can rate this album on. So the maximum scores are maximum scores are 5, minimum scores are 1. Standard deviation is 1.73, which is, in the context of the whole range being 5, is that's a reasonably high value. And that reflects the data, really, because you've got some people, you've got quite a few people giving it a rating of 1. I wasn't one of them, incidentally. You've got quite a lot of people giving, I've never heard the album, I really haven't. You've got a lot of people giving it a 5, a lot of people giving it a 1. So it's a bit of a Marmite kind of album. Some people love it, some people hate it. And the mean is kind of sitting more or less bang in the middle of those, really. So the fact the standard deviation is relatively high shows you the mean's not very representative of the data. It's not really a good fit because the data are actually quite spread out. Opinion is quite divided. Now, if you compare this with one of my favourite albums, which is Iron Maiden's Peace of Mind, same, just downloaded the data from Amazon. And the mean rating of this album is, it's a bit higher than Britney's album. But the important thing is the standard deviation is a lot lower. It's more than half the value, in fact. It's 0.8. And this reflects the fact that there's a lot more consistency in the rating. So the mean is a better representation of the data because basically people gave it 4s or 5s. A couple of people gave it a 2. But on the whole, it gets 4s and 5s, and the mean is sort of sitting more or less between the two. So the data are quite compact around the mean. In other words, the mean is a good fit. So, important things to remember out of all of this are things like sums of squares or mean squares or variance in the context of the mean, and standard deviations basically represent the same thing. The fit of the model to the data. In the case of when the model we're fitting is the mean, they tell us something about variability in the data. But mainly, we should think about these things as how well our model represents. So I think thinking about it in terms of fit, or how well a model represents the data, is the best way to think of what a sum of squares is. And you could also, of course, think of it as error, because that's related. A model that has a lot of error doesn't fit the data well. A model with a small amount of error does fit the data well. So all these kind of ideas are sort of interrelated. So that's basically parameters and model fit dealt with. And you'll be pleased to know most of the other concepts are a bit quicker to explain. So estimation. So if we want to estimate a parameter, like the mean or like the parameters in regression, how do we do it? Now, I don't want to get into the maths of how we do it because we've got computers to do that for us. And, frankly, I don't really understand it. But we can use, basically, the technique that is used is known as the method of least squares. And the method of least squares is reasonably easy to explain without necessarily getting into the maths. So as I mentioned, we've got this basic thing of trying to predict an outcome like the number of friends from some kind of model, and let's stick with the mean as our model. So we've just got a single parameter that we're trying to estimate, and there will be some error attached to that. Now, just as we did when we were looking at deviations, we can rearrange that equation to work out what the error in prediction is. So this is just exactly the same thing as when we looked at deviation. So we can work out the error or deviation by looking at the observed value, how many friends a person actually had, and subtracting from it the parameter, the mean. Now, let's say we didn't have a nice sort of mathematical way to work out what that parameter should be. Let's say we were just guessing. And we said, okay, I think my parameter is going to be 2. So you're just plucking that number out of thin air. You just look at the data, think, yeah, 2. Let's use 2 as the parameter. Let's use 2 as the mean. So what we can do is, again, we look at the actual number of friends that we observed in the data, 1, 2, 3, 3, and 4. Our parameter, which we're guessing at, is, say, the value 2. We can work out the error, again, or the deviation, just as we did before. And in order to add those up and not cancel them out, we square them. So we could work out the squared error. So we know that when we pick 2 as our parameter, the squared error is 7. Now we could say, well, maybe we could do better than that. Maybe we could come up with a parameter that has less error. So maybe you decide that instead of using 2 as your parameter, you'll use 3 as your parameter. And you go through the same process because you're really bored, it's raining, it's a Sunday, it's nothing better to do. You work out the error within that parameter, you work out the squared error within that parameter, and then you add them all up, and then you get a different value to 7. And imagine that you're particularly bored and you had a whole lifetime to spend doing this kind of thing. You could change b to be other values, and you could work out each time what the error is, what the squared error is, and then ultimately what you want is you want the parameter that has the least amount of error. Now, I am that sad, so I got a computer to do this for me. So here's a graph showing you the value of the different values that you could replace with b in that equation. So given the data we had, using different values of b, so I started off with a value of 0 to be my b, and then sort of 0.1, 0.2, 0.3, 0.4, whatever. So I just went through using different values of b, and then working out what the error would be if I used that as my parameter. So what you get on the y-axis is the sum of squared error, so that value of 7 when we used 2 as our parameter. Now what this shows you is you get a nice u. So if you use 0 as your parameter, you get loads and loads of error. As you move away from 0, you start getting less error, less error, less error, until finally you reach the bottom point. So you reach a value of b where the sum of squared errors is the least it can possibly be, and then the error starts to creep up again. So there's actually a point at which the parameter is kind of optimal. It's the most accurate estimate, or the estimate with the least error that you could have. And lo and behold, that value of b turns out to be 2.6. Does that value sound familiar? It's the value of the mean. So the mathematics behind the mean and the mathematics behind working out regression parameters, or any other parameter you might calculate, is based on this idea of minimizing error. So the method of least squares is basically a really hideous equation or algorithm that ends up giving you the parameter for which the squared error is the least. But I just wanted to demonstrate, the thing that I think is important to demonstrate is that you get this curve basically. So if you put in sort of random values for your parameter and work out the error, there will be an optimal value. There will be a curve that descends upon the best estimate, if you like. Now that estimate might not fit the data very well, but it's the best one that you could have given the data you've got. So estimation, for all the tests we use, generally work on this principle of method of least squares. So don't need to know the maths, but just need to get your head around the idea that parameters are always kind of the best guesses that we have, even if they might not be a good fit. Now the standard error tells us something useful about whether a parameter is a good representation of the population. So remember that when we're fitting these parameters, what we're trying to do is actually work out something about the population. So as I said earlier on, we call them estimates because we use values in the sample as a sort of guess of what's going on in the population. Now, if you imagine, so this diagram shows you a scenario that never happens in reality, so this is just sort of hypothetical. If you imagine you had access to your whole population, so that's like the big thing at the top. You've got access to your whole population, you work out that the mean, or the parameter you're interested in, happens to be 3. And let's imagine that you took some samples from that population. So here we've got 2, 4, 6, 8. We've got 9 samples that we've taken. Now, each of those samples, we can work out the mean, or the parameter, and that will be our guess of what's going on in the population. So, for example, you can see the first... Sorry, my symbols have gone a bit squiffy. It's supposed to have a symbol for a mean equals 3. So in the population, our mean's 3, and the first sample we take, the mean is actually 3. It's bang on. It hits the spot. It's exactly the same as the population. That's a happy story. The second sample we take, that has a mean of 2, so it's slightly different from the population. Now, bearing in mind, in reality, we wouldn't know whether it was similar or different from the population. This is just how sampling works. You take a random sample. Some of those estimates will be close to what's actually going on in the population, and some of them won't. But if you were to hypothetically take lots and lots and lots of different samples, and in each of those samples work out what the parameter was, or what the mean was, if that's what you're interested in, you would find that you get a histogram of estimates like this. So what you find is that most of your samples, the majority of samples that you take, will have parameters very close to the parameter in the population. So a lot of them will be quite close to the value that they'll be good estimates. They'll be, what you're trying to get at. But for some of them, they're going to stray fairly far from the mean, and the further and further and further away you get from the true value, the actual value in the population, you start getting fewer and fewer samples that will be a long way away. But you basically get a normal distribution. So this is known as a sampling distribution, and it's a hypothetical entity. It's like a unicorn. They don't really sort of exist, only in a sort of mathematical sense. But it just illustrates the point of sampling, really. Some of your samples will give you very close estimates to the population, and some of them will give you very distant estimates. But on balance, you should get a normal distribution. So most of your estimates will be quite close to the population, but some of them, if you're unlucky, you might happen to get a sample that's very, very far from the population. But we don't know whether we've got a sample that hits the spot or we've got a sample that's quite different from the population. The standard error gives us some idea of whether we have an estimate close to the population or far away. Because all the standard error is basically the standard deviation of this sampling distribution. So if the standard error is big, it means that your sample estimates are very spread out. In other words, it's quite likely that you could have a sample that happens to give you an estimate really different from what's going on in the population. If you have a small standard error, it means that all your sample estimates, hypothetically speaking, are compacted around the actual value, compacted around the value in the population. Therefore, any sample you take is likely to be quite representative of the population value. So standard error is an important concept because by looking at the standard error, you can tell something about whether your sample estimate, so whether your parameter estimate, is representative of the population or not. The small standard error is good, big standard error is bad. Now, related to this are confidence intervals, because confidence intervals are really a way of expressing the standard error. So what you do is you take your estimate, your sample estimate of the parameter. That could be a mean, it could be a regression coefficient, whatever. And then you add a couple of standard deviations either side, and it gives you this interval estimate. So this is an example of sperm. Seems to fit the penis theme. So there was a study done in the late 90s by a group of people, and they were looking at conditioning in Japanese quail. So the idea was it was kind of evolutionary psychology in quails. So you had like a male quail in a box. I assume that's what male quails do when they're in a box. And a female quail in a chamber with a door. It's a bit like a nightclub in a way. So you'd get your male quail, and every so often they'd flash a light, like a red light, and when that light flashed, the door opened and the male quail could wander in and go and chat up the female quail. So they did this lots and lots of times. So the red light was acting as a signal to the male quail that there was a mating opportunity. And then after lots and lots of trials, what they did was they allowed the male quail to actually mate with the female quail. Except they played a bit of a trick on him, and because they wanted to collect his sperm, so on the actual mating trial, they put a fake female quail. It was like a sort of cagey thing that had a taxidermied head on the top. Now, I think this tells you all you need to know about males, but it didn't really put him off. He did the job, and they counted the sperms. Anyway, what they showed was that if you'd had these conditioning experiences, so if you'd had a signal that told you when there was going to be a mating opportunity, basically the amount of semen that the quail produced was affected. So knowing that you could mate affected the amount of semen that they actually produced. So they were sort of conditioned to produce more sperm, essentially. Anyway, so coming back to this, imagine in a kind of really perverse world where you really like to torture male quails, you did this experiment like 100 times or something. Like I say, this is hypothetical, you'd never actually do this in reality. Each time you do the experiment, you would have an estimate of the amount of sperm that a quail produces. Now, I've got no idea. I don't know how many sperms a quail produces. I think there are some things in life I can go to the grave not knowing, and it's fine. A male quail sperm counts as one of those things. So I don't know, but I guessed randomly that it might be around, say the population value is 15 million sperm. That's how many sperm you'd expect a male quail to produce. So in a given experiment, what you're going to do is come up with a point estimate of how many sperms they produce. So that might be 17. So it's different from the population value, but you don't know it's different because you don't have access to the population. But you construct a confidence interval around it, and what that does is that tells you, rather than having a point estimate, it gives you a sort of a range of values within which the population value ought to fall. Now, the important thing about confidence intervals is they are constructed in such a way that assuming it's a 95% confidence interval, 95% of the time, the interval will contain the population value. So what this illustrates 50 different experiments. Imagine you did 50 experiments. In each experiment, you calculated the average amount of sperm and a confidence interval around it. Then basically 95% of those intervals will contain the true value. So the true value, which you'd never have access to, is the dotted line going down the middle, which if I had my nice pen thing, this thing. I'm forgetting I'm tall-ish. So this is the value you're trying to get. Now you can see like this first interval at the bottom, that contains the population value. It contains 15 million sperm. The second experiment, the confidence interval contains the population value. The third experiment, the confidence interval contains it. There's 3 that don't. So if you look, there are 3 intervals highlighted there that miss the population value. And this would be representative of roughly a 95% confidence interval, because that's 3. It should be 2.5 out of 50, but I couldn't do that diagrammatically. So around 3 out of 50, or around 5 out of 100 will miss the spot. So a 95% confidence interval tells you basically the interval in which the population value is likely to fall, and you know that it will fall within that interval in 95 out of 100 samples, if you like. So if you want to make the assumption that your sample is one of the 95 out of 100, for which the confidence interval hits the spot, you can use the confidence interval to tell you, well, that's probably, the population value, the value we're trying to actually estimate is probably somewhere in that range. Now, you might be unlucky. You might happen to have one of the 5 in 100 intervals that doesn't contain the population value. But we set this value of 95% deliberately high so that, we feel, reasonably sure that we can interpret that as an interval within which the population value falls. So confidence intervals and standard errors are related. And the thing is, because we know that confidence intervals tell us something about the value in the population, if we look at different confidence intervals in different groups, we can tell something about whether they come from the same population or not. So for example, looking at the top of this diagram, where the confidence intervals don't overlap, what that's likely to mean is that the population estimates of those 2 samples don't overlap. And the natural conclusion from that is therefore that they don't come from the same population. Their parameters are so different that the population values don't even coincide at all. then that probably means they're from different populations. So when you look at sort of error bar graphs with confidence intervals on, the confidence intervals don't overlap. Basically, that means that the groups are from different populations, or whatever you've done to the different groups has had some kind of meaningful effect. Now, actually, confidence intervals can, if you look at the bottom of the diagram, they can overlap a little bit and still represent significant differences between groups. So it's a bit of an oversimplification to say if they don't overlap, there's a difference, and if they do overlap, there's not, because actually you can have a little bit of overlap, and that can still represent a sort of a significant difference between those parameters. But the point I'm trying to make is just that confidence intervals tell us visually something about whether two samples are likely to be from the same population or not. So again, related to this is the idea that we could significance test parameters. So any parameter, whether it's a mean or whether it's a regression coefficient or whatever, there's a distribution associated with it, a probability distribution. And we can use these distributions to work out whether a particular value we've got is likely or unlikely. So the distribution just tells us, is the value we've got particularly high given the properties of this parameter or statistic? So this is the significance testing that you will have come to know and love. So normally we use this p-value. So a lot of the time when we look at significance tests, we just use this criterion of 0.05. If our p-value is less than 0.05, what that means is that it's very unlikely that we would have got the value of the parameter that we got if there wasn't an effect, essentially. So if there wasn't an effect, we shouldn't have got a parameter as big as the one we have. Therefore, we assume that there's something significant going on, a significant effect. So this is what those of you that did research skills would have spent a lot of last year doing. So looking at significance tests, looking at p-values, and if the p-value was less than 0.05, you go, hooray, we've got a significant effect, throw a little party, and get very excited. However, there are some problems with significance testing, so I want to just show you a couple of scenarios. So the first scenario is, so we go back to the cloak, having an invisibility cloak, and whether that makes you more mischievous. So imagine we have one group who have no cloaks, no invisibility cloaks, another group who have invisibility cloaks. We measure how mischievous both of the groups are, and we're interested in whether there's a difference between those two groups. So here's an output of two t-tests. So this is just a test saying, is the mean in our no cloak group different to the mean in our cloak group? Now look at those two values. The mean difference between the groups, so literally mean 1 minus mean 2, is 2.21. It's exactly the same. So the mean difference is the same in these two examples, but in one example, we've got a significant value. In the top example, our p-value, our sig, is less than 0.05, so it's significant. But in the bottom example, our sig is bigger than 0.05, so it's not significant. How can that be? It's the same difference, but in one case we're being told it's a significant difference, and in another case we're being told it's not. The answer is that significance is entirely dependent on sample size. So the top example is based on a sample of 200, but the bottom example is based on a sample of 10. So as your sample gets bigger, you have what's known as more power to detect differences between groups. So the differences between groups are, more easily detected. But you can take this to a ridiculous extreme. So the bottom example, we have a mean difference of 0. There's no difference between the groups. I mean, actually, there is a very small difference, but if you round it off, it's a difference of 0. The mean of one group is almost identical to the mean of the other. So that should be completely non-significant, right? Because the groups have the same mean. But actually, we get a p-value of 0.02, which is less than 0.05, so we would say it's significant. Surely, that's a ridiculous scenario to have no difference between groups but a significant effect. And the answer is, to why this happens, is we have this is based on a huge sample. So this is a sample of 1 million people, which of course you'd never have. But the point I'm trying to illustrate is that significance testing can be misleading. If you have big samples, you can end up with very, very small effects that appear to be important. And if you have small samples, you can end up with quite big effects that are deemed non-significant. So it's not a perfect process. So sometimes it can be useful to, rather than rely on significance testing, use something called an effect size. And the effect size I want to tell you about is Cohen's D, because it's very straightforward. But when we talk about regression, we'll also and over a bit, we'll also talk about R. So an effect size is just a way of expressing an effect in a sort of a standardized way. In the case of looking at differences between groups, it quite literally is the difference between the mean of the experimental group, the mean of the control group, divided by the standard deviation of the control group. So it's experimental minus control over the standard deviation of the control group. There's a slightly more sophisticated version, which is a bit scarier. But all that's saying is sometimes it doesn't make sense to use the standard deviation in the control group. So instead, you take an average standard deviation, essentially. So the big equation at the bottom is just looking at, it's basically just the variance of each group. It's weighted by the sample size, but essentially that S pooled, it's kind of like, it's a bit like the average standard deviation of the two groups. Now to go back to this cloak example, if we actually work out the effect size, so we've got the two means in the table, so we take the difference between the means and divide it by the standard deviation of the control group, we get an effect size of 0.83, that's actually quite big. If we use the pooled estimate, we get an effect size of 0.88. So it doesn't, in this example, it doesn't matter too much which version of D we use. The point I want to illustrate here, I know I'm whizzing through the equations, but that's because that's not the important thing. The important thing is that if we work out the effect sizes in these three scenarios again, they are much more representative of what's actually going on. So the first two examples, where the difference between means was pretty similar, we get very similar effect sizes. We get a D of 0.88 and a D of 0.96. They're pretty similar. And in the scenario where there was no difference between groups, we get a D of 0. We get no effect, essentially. So it's much less misleading than significance testing. So I'm going to end it there. The main point I want you to take home is we've got these 5 key concepts. In terms of significance testing, bear in mind that sample size makes a difference, and also bear in mind that we can use effect sizes to give us a more accurate representation of what's going on when we look at whether a parameter is sort of significant or not. It can be better just to kind of quantify it as an effect size. Okay, so tomorrow I'm going to see you at 9 o'clock, and we're going to start talking about assumptions and bias when we explore data.